Good morning, my dear students. Our chapter number 6 is going on, which is electric circuit. Okay. In this chapter, yesterday we discussed about applications of some applications of potentiometer, and in this sequence, our important application is determination of a internal resistance of a primary cell. This is very important application of potentiometer. Today, we are studying a new application, which is measurement of small resistance. Measurement of small resistance. Okay, by the help of a potentiometer. Firstly, we draw the circuital diagram of a potentiometer. First, we draw primary circuit of potentiometer. I speak the structure and plot the diagram. Okay. Now, suppose we have a potentiometer and a cell. This is wire of potentiometer A B. Okay, a cell of EMF EP and a key K1 rheostat RH1 is connected in series sequence in a primary circuit. This is primary circuit of a potentiometer. This is remains same in all applications, so learn it carefully. This is a cell EP, this key K1 and rheostat RH1. Now in secondary circuit, a resistance, we take a non-resistance, this is capital R, a unknown small resistance, this is small r, and a rheostat RH2, a cell of EMF capital E, a key K2 are connected in series sequence, in series order, and a higher potential end of this capital R resistance is connected to point A, and a lower potential end of both resistances capital R and small r connected to two-way key. We know that two-way key, this is a two-way key. In this key, three terminals are present, which is represented by X, Y and Z. Two terminals are input and one is output. Okay. So we can say to lower potential end of a capital R and small r connected to XZ terminal of a two-way key and Y terminal of this two-way key is connected to galvanometer, and another end of galvanometer is connected to a jockey Z. Okay, this is the circuital diagram of a potentiometer. By this diagram we measure small resistance. Okay, now working of this application. Okay, firstly this key K1 is closed, then due to this current flowing through this primary circuit. Okay, now key K2 is also closed, then in this sequence the current flow this secondary circuit. Okay, now a plug, a dot is inserted between the terminal X and Y of this 2VK. Then in this condition, this R is connected with this galvanometer. Due to this galvanometer shows the deflection. So for zero deflection, we slide this jockey on the wire of potentiometer. Now we find zero deflection. Now we find zero deflection by moving the jockey on this wire AB. In zero deflection, balancing length, suppose L1 for this resistance capital R. For this resistance capital R, balancing length is L1. Okay, and potential difference, suppose that this is V1 across the end of this resistance capital R. Then in this situation, according to principle of potentiometer, what is principle of potentiometer? According to this principle, in zero deflection state, the unknown EMF or unknown potential difference is equal to non EMF or non potential difference on this wire. Okay, so according to this principle, if potential gradient of this potentiometer is X, this is potential gradient. What is potential gradient? Voltage drop per unit length is equal to potential gradient. This is represented by X. Okay, this potential drop per unit length and total length of this balancing length of this wire is L1. Then in this situation, suppose V1 is the potential drop or potential difference across the end of this resistance capital R. Then according to principle of potentiometer, V1 is equals to X into L1. This is the potential difference. Okay. We know that Ohm's law. What is Ohm's law? Ohm's law is the potential difference across the end of this resistance is equal to multiple of this resistance and current flowing through this resistance. Means according to Ohm's law, V1 is equals to I into R. Okay. So from these equations, I into R is equals to X into L1. This equation number 1. Okay. Now in this two-way key, we remove the plug between from the X and Y and plug in between Y and Z. In this situation, the total resistance capital R plus small r, these are the connected in series. This connect with this galvanometer Z. Then in this situation, again this galvanometer shows the deflection. Now we find again zero deflection in this galvanometer. In zero deflection state, suppose L2 is balancing length for this capital R and small r resistance, and potential difference across the end of resistance capital R plus small r is V2. Then in this situation, again by the principle of a potentiometer, V2 is equals to X into L2. And again, according to Ohm's law, V2 is equals to I into R plus small r. I is the flowing current through these resistances, and we know that in sequence electric current remains same. Okay, from these equations, I into R plus R is equals to X into L2. This is equation number 2. So from equation 1 and 2, I into capital R plus small r upon I into R is equals to X into L2 upon X into L1. I to I cancel out and X to X cancel out. Then dividing above term from below term, then we get 1 plus small r upon capital R is equals to L2 upon L. You find small r, then transfer this one in RHS, then we get small r upon capital R is equals to L2 upon L1 minus 1. Take LCM of RHS, then small r upon capital R is equals to L2 minus L1 upon L1, and unknown small resistance small r, we get L2 minus L1 upon L1 multiply R. This is the equation of unknown small resistance. In this sequence, we put the value of L1, L2 and capital R, then we find the value of small r. Here, capital R is non-resistance, this is non-resistance, and L1 is balancing length for resistance capital R, and L2 is the balancing length for capital R plus small r resistance. Now such type we find the small resistance by the help of a potentiometer. Okay, this is the another application of a potentiometer. This is very important for our annual examination, and this is also used in our practical examination and our numerical questions. Okay, so learn it carefully and remember this expression for small resistance. Okay, now we take some example, some numerical question of this chapter. This is question number first. This is our first numerical question. This is based on Kirchhoff's first law. Find electric current I in the circuit shown in figure. This is an electrical circuit, and in this circuit we determine this electric current I. This numerical question based on Kirchhoff's first law. What is Kirchhoff's first law? Kirchhoff's first law is, in any electric circuit, the algebraic sum of a current at any junction point must be 0. It means summation I is equals to 0. And here we applying sign convention rule, which is, if a current is enter in junction point, then it is positive, and then current is outward direction, then current is negative. Okay, so for point A, junction point A, this current in the direction inward direction, then this is positive 5 plus this also in inward direction, this positive 2. This is outward direction, then this minus 1.5, and this also minus x is equals to 0. This is the algebraic sum of a electric current on this junction point. Okay, now then from this equation, x is equals to 5 plus 2 7 minus 1.5, then we get 5.5 ampere. So x is equals to 5.5. Then at point B, 5.5 ampere in inward direction minus this is outward direction, so minus 2, and this also outward direction, this minus y is equals to 0. Then y is equals to 5.5 minus 2 is equals to 3.5 ampere. So value of y is equals to 3.5. So at point C, from the Kirchhoff's first law, y inward direction, so 3.5, and this is outward direction, so minus 0.5 ampere, and this also outward direction, I is equals to 0. According to this equation, I is equals to 3.5 minus 0.5, this equals to 3 ampere. This is the current I, value of current I. This is very important. This type of question is very important for our annual examination for 1 mark question. Okay, so more questions of this type, and if you have any problem, then you comment your problem in comment box, and share this video and like this video and give feedback about this video. Thank you.